Okay, so this is the last meeting of combinatoric seminars this term, and we chose the topic very carefully. So this is the speaker is Larry Guth from Toronto and IES, and he will show us that n points in the plane determine nearly n distinct distances.
Okay. Well, thanks for having me. I'm excited to talk about this. Okay, so suppose we have a set of points in the plane. This is n points. And then we think about the different distances between those points. So d of p is the set of distances p minus q, where p and q are points, and let's say p is not q. And there's a conjecture of Erdos that the size of this set should be at least, so pretty close to n, log of n to the minus a half. And recently, something close to this was proven, namely that d of p is at least a constant times n log of n to the minus 1. OK, so when I put a norm around a set, that means the number of elements in that set. And so this theorem was proven by Netz, Katz, and myself, building on work by Elekes and Sharir. Actually, I'd like to say Netz was really the driving force behind this. At some point, he was stuck on something, and he came, and we had some conversations, and he included me in the paper. But this is mostly his work, building on this, which is great. And I'll show you. OK, and this is a pretty substantial improvement over previous lower bounds. So previously, one knew things like d of p is bigger than n to some power. And the best power was 0.86, which is Katz and Erdos. And there's a sequence of people contributing ideas to make this power larger. OK, so to get a sense for this problem, let's think about some examples of point sets. So 0 is generic points. So if I just pick n points with no relationships between them, no two of those distances will be the same. So the size of this set will be n choose 2. Every pair of points will have a different distance. And unless you do something special, that's what will happen. But it's not hard to think of examples that are much better than this. So example 1 is I'll call a line, which is evenly spaced points on a line, like, for example, 1, 0, 2, 0, and so on, up to n0. And then it's easy to see that the distances between these points are integers from 1 to n. So this is n minus 1. And then it's possible to do a little bit better than this, which was Erdős' idea. Namely, you do a little bit better if, instead of putting the points on a line, you put them in a two-dimensional grid. So take a square root n by square root n square lattice. So if you do that, I'll draw a little picture here. If you do that, then the distance set has the form square root of a, where a is x squared plus y squared, and x and y are integers between 0 and the square root of n. So that means that a is going to be between 1 and 2n. X and y are integers. That gives you around n choices of a. But we have a little bit of extra information, namely a are only integers which are of the sum of the form which are the sum of two squares. Not every integer is the sum of two squares, so this cuts down on the choices a little bit. And Erdos figured out what happens in this example. Where should I write it? So and what comes out of that is, this number here. you get around n over the square root of log of n different distances by cutting down to the numbers which are sums of two squares. OK. So the next thing I wanted to do is to try to draw a picture of what would happen if the distance set was significantly smaller than n. So I'm trying to make a picture. So suppose that the size of the distance set is n to the 1 minus epsilon.
Sorry, I missed just the punchline. So what is d of a in the grid?
D of p in the grid is n over the square root of log n. OK, so let's try to imagine what this set of points would look like if the number of distinct distances was n to the 1 minus epsilon. Well, I'll draw a first point. And now there are essentially n other points. But there are only n to the 1 minus epsilon distances. So I can draw n to the 1 minus epsilon circles around this first point. Let me say that the distances are d1 less than d2 less than whatever. So this circle here has radius d1. There are n to the 1 minus epsilon circles, and all of the points need to be on those circles. And there are n points, so typically there are many points on each circle. OK, that's not a huge deal yet. It would be easy for me to draw many points on each circle. I'm going to hold off on doing that for a second. So now let me consider another point. So there's some point on one of these circles. And around it, I'm also going to draw a circle of each of these radii. Looks something like that. So all of the points in my set need to lie on a white circle, and they also all need to lie on a red circle. Also all need to lie on a red circle. So OK, so for example, I might have points all along here, and so on. So I have some set of points like that. And now if I keep doing this, I'll eventually have for each point and each other point, there'll be a circle centered at that other point through this point. So if I keep doing this, each point is going to lie on n different circles. So through here, this is going to start to look like that. OK, so a first reaction is that there are circles that manage to have a lot of points of high intersection. And you might begin by wondering whether that is possible. So what we see kind of quickly is that we have n to the minus 2 epsilon circles. We have n special points which lie on at least n circles. So question 1, is this possible? Yeah. And so I don't know whether this is possible. I believe that this is a deep open question about how circles overlap. But some things about it are known. And basically, all of the previous attempts to make progress on the distinct distance problem have been by studying how circles can overlap in this kind of question. So one of the best results that came out of that is this theorem of Solomosi and Toth, which says that so P is a set of n points in the plane. Then I can choose one of the points in P. And then if I look at the distances P minus Q, this thing, the size of that set is at least like n to the 6/7. So in particular, the size of the whole distance set should be like n to the 6/7. And this was more or less the last real breakthrough in the study of the Erdos distance problem, the distinct distance problem. OK, so yeah.
6/7 is accidentally very close to the 0.86.
Yeah, so 0.86 is a small improvement of 6/7, and I should check whether they also have this, you can find one point with this many distances or not. But that's a refinement of this method. OK, so the point I want to make about Solomossi and Toth is that, OK, they're using, their argument is using that there aren't too many distances with each center separately. So we're using the fact that this distance is the same as that distance is the same as that distance. We're using the fact that this distance is the same as that distance. But what they're not using is the fact that this distance is the same as that distance. So the new ingredient is that Elekes and Sharir thought of a way of using the fact that this distance is the same as that distance. There's a lot of extra information of that form because there are only like n to the epsilon points on each circle. So there's not too many. So just saying that this is the same as these is relatively weak compared to the much stronger statement that this is the same as that, is the same as that, is the same as that. Right? There's a lot of extra information there, but it's really tricky to figure out how to use that information. OK. So now I'm going to show you Elekes' idea about how to use that information, that distances involving just involving 4 completely separate points are the same. So chapter 1, partial symmetries. OK, so let G denote the group of orientation-preserving rigid motions of R2. So this is a 3-dimensional group. It's generated by a 2-dimensional group of translations and a 1-dimensional group of rotations. So one thing you could think about is the symmetries of P. So the symmetries of P is the set of G and G so that GP is equal to P. That's a natural thing that people think about all the time. But of course, many sets of points will have no symmetries. But Elekes had the idea to think about what I call partial symmetries, namely rigid motions that move a significant chunk of P to P. So G sub k is going to be defined to be the set of rigid motions G and G, so that if I look at GP intersected with P, it's at least k. There are, in other words, at least k points in the set P, which after I perform this rigid motion are still somewhere in the set P. OK, so G1 is an infinite group, and it's an infinite. Sorry, it's not these are not groups except for the symmetry group. G1 is an infinite set, which won't be that interesting to me. But G2 is already a finite set. And then this condition is clearly getting stronger, so I have G2 contains G3, contains, and so on, contains Gn. And Gn is the ordinary symmetry group. OK. So I think it's a natural question for a set of n points, how big may be the set G sub k of partial symmetries? And that question was raised probably for the first time in Elekes and Sharir's paper. And they made the following conjecture. Elekes and Sharir, that the size of gk should be less than or equal to n cubed k to the minus 2. So this turns out to be true. And to motivate their conjecture, Elekes and Sharir proved it for k equals 3. And Katz and myself proved it for all k, so for k greater than or equal to 2. So I should say here we have if k is at least 2 and at most n. So if k is 1, that's not true. There are infinitely many. But if k is at least 2, that is true. And if k is bigger than n, gn just doesn't make any sense. OK, so this is true. And it's also sharp up to constants. And the example where it's sharp is for the square lattice that Erdos introduced at the beginning of the problem. OK. So what I'd like to do next is to explain to you how the partial symmetry, and in particular that conjecture, is related to the distance problem. And this is fairly elementary, but at the same time, I think a really nice observation of Elekes. It's relatively simple, yeah.
It's the same fact that the popular lines contain about 10 to the 1/3 points or something.
I'm not sure if it's the same as that, but it might be. Yeah. So if I have my lattice here, and if I want to perform a rigid motion so that I still keep a lot of points in the lattice, then I should do the following thing. I should pick a box here of dimensions root n over root k, which I'll justify in a second. And then I should perform a rotation so that 2 of the elements in this box go to 2 other elements in this box. And then if I do that, because I have basically a k by k grid of boxes of this size, and basically the same thing will be happening in every box. So I have a root k by root k. I have k of these boxes. And so if I perform a rotation so that 2 elements of this box land in the lattice, then 2 elements in every other box will land in the lattice. So I'll have about k elements landing in the lattice. And then you can count the number of ways of doing this, and it comes out like that.
Box does not have to go to itself, but maybe to another box.
Yeah, that's right. Sorry. So you should choose a rotation like this, and then you should translate. Yeah.
Is there a big distinction between getting examples that are sharp for every case simultaneously and getting it sharp for different examples for different k?
Yeah, right. So so for the square lattice, which has root n by root n points, this is sharp up to a constant factor for every k. So yeah, for all of these k's. Yeah. OK. So let me explain to you how these are related. Yeah, there are some things known, but to be honest, I'm not even up to date about what happens in higher dimensions.
Yeah. So you can check what the grid gives. It's a different power, right? So it's n to the 2 over d, I think, for the conjecture, right? Power. Just an n to the 1 over d by n to the 1 over d, and so on.
So this gives. Yeah. So I don't have any progress to report on that because, well, at several points the proof will not easily generalize. OK. So to connect partial symmetries to the original problem, Elekes introduced the set of distance quadruples, Q of p. It probably appears in lots of places. So this is sets of points p1, q1, p2, q2, which are all in p, with the property that the distance from p1 to q1 is equal to the distance from p2 to q2. And let's say that it's not 0, though it's not that important. So then the clever thing that Elekes observed is that we can count these quadruples in two different ways. One of them is going to be closely related to the number of discrete distances, and one of them is going to be closely related to the number of partial symmetries. So let me begin by counting them in terms of partial symmetries. So the number of quadruples can be written as the sum k equals 2 to n of the size of g exactly k times k choose 2. Now g exactly k, I should maybe have defined up here. Right, so gk is groups that preserve at least k points, but g equals k is the set of rotations so that gp intersect p is exactly equal to k. OK, so Q of p, the number of quadruples, can be counted that way. And here's the proof. So if I have a distance quadruple, so if p1 minus q1 is equal to p2 minus q2, and it's not 0, then there's a unique rigid motion, g in g, such that g of p1 is p2, and g of q1 is q2. So here's a picture. So I have a point p1 and a point q1, and somewhere I have p2 and q2, and all I know is that this distance is the same as that distance. And then I can take a rigid motion. First I can say translate p1 to p2, and q1 will end up here. And then I can rotate until q1 coincides with q2. There's my rigid motion, and there's only one way of doing that. OK. So in other words, this tells me that there is a map. Q of p gets mapped to g. Every quadruple is assigned to a rigid motion. And so now I can count the quadruples by going through the rigid motions, and for each rigid motion, seeing how many quadruples have been assigned to it. Well, now suppose that g is a rigid motion. How many quadruples are assigned to it? Suppose that gp intersect p is k. Means there are going to be k points in p that will be mapped to other points. Then this number is k choose 2. So maybe I should make a picture of that. Well, OK. So if I take any 2 points in p intersect gp, and then I push them forward by g, I'll get 2 other points of p, and the distance will be preserved. So that'll be a distance quadruple, and vice versa. So the number of points assigned to each rotation is k choose 2. And therefore, I can count Q of p this way. OK. So now, if I know this conjecture, which we'll talk about later why it's true, then I can plug it in. And it will allow me to bound this tricky thing. And I'll get some upper bound for Q of p. So in order to do that, I have to massage just a touch. So this is the sum k equals 2 to n. So g exactly k in my old notation is gk take away gk plus 1, k choose 2. Right. And then if we expand this out and cancel, we get the sum k, we get at least approximately the sum k equals 2 to n of gk times k. So this gk will appear at this step multiplying k choose 2, but at the previous step it was subtracted multiplying k minus 1 choose 2. And when you group those terms, you get approximately gk times k.
The boundary effect, you don't worry about those. Kind of at the beginning and the end or something.
Yeah.
Probably
Yeah. Yeah, thanks. OK. And then we just plug in our bound. This is less than or equal to the sum n cubed times k inverse, k equals 2 to n. So this is n cubed times log of n. So the number of distance quadruples is at most n cubed times log of n. And these things were sharp for the square lattice. So this is actually also sharp for the square lattice. OK. So that was one way of counting quadruples in terms of symmetries. And there's another, I would say, more obvious way of counting the triples, counting the quadruples, which is in terms of grouping them by their distances. So let me say, again, that the distances are d1 less than d2 up to dA, where a is the number of distinct distances. So then I can also write the number of quadruples as the sum I equals 1. Oh, I need another piece of notation. So for each distance n of I, for each distance di, n of I is going to be the number of pairs pq, so that the distance from p to q is that distance d sub I. So for each distance, I count how many pairs I have at that distance. And then the number of quadruples is the sum I equals 1 to a of n of I squared. So for each quadruple, the distance from p1 to q1 equals the distance from p2 to q2. And I'm going to sum over those distances. So I sum up over those different possible distances. And then for each distance, I just have to choose 2 different pairs at that distance. The number of ways I can do that is n of I squared. OK. So that's n of I squared. Now, I don't know a lot about the n of i's, but I do know that the total number of pairs is n choose 2, which is the sum of the n of i's. So at this point, I can use Cauchy-Schwarz and say that this is at least 1 over a times the sum I equals 1 to a of n of I all squared. This is Cauchy-Schwarz. And now the sum of n of I, this is just the sum of all of the different pairs. This is n choose 2. So this is n choose 2 squared over the number of distinct distances, which is essentially n to the 4th over the number of distinct distances.
So here there is a place where maybe there is a loss because possibly the ni's cannot be equal to each other.
Yes, that's right. Yeah. So right here, we could have a loss if these are not equally distributed. And that, in fact, occurs for the square lattice. Yeah. OK. Well, now let's just put together the information we got from these 2 ways of writing Q of p. We have that the number of quadruples is at most n cubed log n from thinking about them using symmetries. And it's at least n to the 4th over the number of different distances. And then we can easily rearrange this to say that the number of different distances is at least n over log n. And there's some constant. OK. So that's how these partial symmetries are related to the number of just different distances. And it's pretty elementary, but I think a really clever and nice idea. I think it was the first idea where someone was seriously able to take advantage of the I erased it, but distances at points at 4 totally different points being the same. A way of using that. OK. So it suffices to try to prove this conjecture about the number of partial symmetries. And this conjecture may not look like anything one has seen before, and it's not at all obvious that this is going to be any easier than the original problem. But Elekes had another idea about how to think about this, which connects it to an area where there are some theorems and some techniques, namely connecting it to incidence geometry. OK, so connection to incidence geometry. OK, so inside of my group G, I'm going to look at some sets, L, P, Q. So P and Q are points in my set of points. And this is the set of rotations so that G of P equals Q. OK. Now, this G is a three-dimensional group, as I mentioned before. And for every P and Q, LPQ is a one-dimensional curve. So if I know that my rigid motion has to map P to Q, then it's determined up to performing a rotation afterwards. So I have a circle, or one-parameter family of different traces. So this is a one-dimensional curve sitting in G. OK. And then Elekes observed that a rigid motion is in GK if and only if G lies in greater at least K of the curves LPQ. So this is really just the definition, but I'm going to make a picture anyway. So let's say that this curve here is L P1 Q1. This curve here is L P2 Q2. And this curve here is L P3 Q3. And this point here I'll call G. It lies in all three of those curves. Well, just by definition, I know that G of P1 is equal to Q1, G of P2 is equal to Q2, and G of P3 is equal to Q3. Those are just the definitions of what it means for G to lie in those curves. So that tells me that if I look at G of all of the points intersected with all of the points, it's at least 3, because G of P1 is in there, G of P2 is in there, and G of P3 is in there. Now, there is something a little, one should actually say a little bit more than that, right? Because we want to, if P1 and P2 were the same point, this argument would not work. But if P1 and P2 were the same point, then G would have to map them to the same point. So Q1 and Q2 would have to also be the same. And if P1 is the same as P2 and Q1 is the same as Q2, there wouldn't actually be two different lines here. There would just be one line, one curve. So this is kosher. OK, so these partial symmetries, GK, that we're interested in counting are rigid motions where a lot of these curves are going through them. And this is reminiscent of incidence geometry, where one studies, say, lines in R3 and points that have a lot of lines going through them. So Elekes and Sharir made a metaphor connecting this problem about these kind of special curves inside of the group G to more traditional problems about lines in R3. And next, Katz found some coordinates that tighten up this metaphor and make it just kind of literally true. So Katz's coordinates do the following thing. So inside of G, there are some translations. So rigid motions that have no rotation but just translations are sitting in there. And then the leftover is G prime. It's defined to be G without G translations. And Netz found some coordinates so that G prime in these new coordinates is just R3. And an LPQ in these new coordinates is just a line. And if I keep P, but I have two different Qs, LPQ1 and LPQ2, these correspond to skew lines. G prime corresponds to R3. So remember that G prime is the rigid motions without translation. OK. So this is a minor point. I was considering suppressing it. But it's not plausible. The group G is not homeomorphic to R3. So it's not plausible to just have coordinates that make G into R3. But if you remove this rather small set of translations, then the leftover bit is homeomorphic to R3. And there are nice coordinates that turn the curves we're interested in into lines. OK. Moreover, the translations are a very small subset of all of the rigid motions. And so we'd like to bound GK both for translations and for the other guys.
So this is just a set theoretic subtraction?
Yes. Yeah, this is just, right, this is a set theoretic subtraction.
So what you have left is things which are not just a translation. You can translate and rotate. That's OK.
Yeah, exactly. Yeah. OK, so now separately, we'd like to bound the number of partial symmetries that are just translations and the number of partial symmetries that are not just translations. And there aren't very many translations, and so it's elementary to bound the number of partial symmetries that are translations by what we want. So I'll just say it's easy to bound G translation intersect GK less than or equal to n cubed k to the minus 2. OK, so we're left over with the GK elements in G prime, which we can think of as points in R3 that have a lot of lines going through them. OK. So that led Elekes and Sharir to make a conjecture about points, basically a conjecture about points and lines in R3. And that was what Katz and I were able to prove. OK, so I'm going to call this Theorem 2. It says that if I have a set L of n squared lines in R3, and then if Sk is defined to be, and there are at most n lines in a plane, and Sk is defined to be the set of points that lie on at least k lines, and k is between 3 and n, then the size of Sk is less than or equal to n cubed k to the minus 2. OK, so this might take a little digesting. I have a set of n squared lines in R3. There are, by the way, there are n squared of these LPQs, so that matches up. And at most n of them lie in a plane. Well, if I pick a plane, so if I fix P, then LPQ1 and LPQ2 are skew to each other, which is easy to check if you bother to write down these coordinates, but it's a little bit of a pain to write them down. That means that these are not both in any plane. So if I fix a plane and I look at the lines in it, I'll have P occurring in at most one of the lines. And that means I'll have at most n of them in a plane. So this will actually be true for the lines that we're considering. And then I look at the points that lie on at least k lines, and those correspond exactly to the partial symmetries. So a rigid motion is in GK if and only if it lines on at least k lines. And k is between 3 and n. Then the size of the set of points obeys the estimate that I want. So this implies the partial symmetry conjecture for 3 less than or equal to k less than or equal to n. Yeah, this is like an extension of the joints, and I'll come to that in a minute. OK, so this was proven by Elekes and Sharir for k equals 3, and then by Katz and myself for all k as stated. The partial symmetry conjecture is for 2 less than or equal to k less than or equal to n. So this doesn't prove quite all of it. One also has to prove k equals 2. So Katz proved k equals 2 in a somewhat related but separate argument.
For k equals 2, you just have to prove that it's n cubed, right?
That's right. That's right.
In the whole size of the group, the n cube is not simple.
No, the n cubed is not simple.
Okay.
Yeah. Yeah. So there are sort of 2 sections of our paper, one explaining what to do when k equals 2, and the other explaining this theorem, what to do when k is at least 3. And they have different ideas, and I decided that it's not reasonable to try to present both of them. So I picked one of them, which subjectively to me might be a little more interesting, although people could disagree. Anyway, I'm just going to tell you about that. Yeah?
Is it easy to say what the picture is for theorem 2 when it's the grid? Like what the lines look like? Or?
Yes. When P is the grid, then the lines look like the following thing. So I'm going to say P0 contained in R3 is the set of A, B, 0, where A and B is in P. And P1 contained in R3 is the set of CD1, where CD is in P. So I just take 2 copies of this grid, one on top of the other. And then L is the set of lines from a point in P0 to a point in P1. So I have endpoints here and endpoints there, so I get n² lines. And those are the lines. Yeah. And then we computed. So then we computed it for this set of lines. That theorem is sharp. Yeah. OK. So this is a theorem in incidence geometry, a theorem about points and lines and how many times they intersect. And I wanted to do a little review of incidence geometry and mention 2 important theorems. And that will put this into context. And also we'll need those ideas to understand the proof of that. So my plan is to do a little review of incidence geometry and tell you the major theorems. And then we'll be ready to take our break. OK. OK. So the most important theorem in incidence geometry is the Szemeredi-Trotter theorem from the early 80s. And it's the 2-dimensional version of this kind of problem. And so it's simpler and more fundamental. So it says that if L is a set of L lines in the plane, and I look at the points that have a lot of lines through them, so these are points that lie on at least k lines, then the size of this point set is bounded by L squared over k cubed plus L over k. And there are two terms here, and depending on the value of k, one or the other of them is more important, and it's easy to check which is which. So, and it's helpful to know that. So if 2 is less than or equal to k is less than or equal to the square root of L, then the first term dominates. And that's always going to be the situation that we're in this talk. And that's also the hard case of the theorem to prove. OK, so let me give a little background about this theorem. Probably many people have seen it, but probably many people also haven't seen it, or at least in a while. So the first thing to say about it is that there's an easy bound. The easy bound is that sk is bounded by L squared over k squared. And the reason for the easy bound is as follows. At every point of sk, there are k lines going through that point. So there are k choose 2 pairs of lines that intersect. And in total, there are only L choose 2 pairs of lines, and any pair of lines only intersects once. So sk is, by that argument, absolutely less than L choose 2 over k choose 2, which is basically that. OK, the next thing that's important to know is that this easy bound is the best thing that's true in finite fields. So if I work in f sub p is the finite field with p elements, p is a prime. If I work in there, this easy bound is optimal, at least for some values of L and k. Namely, I could consider the following thing. I could look at all of the lines in this finite field. So L equals all the lines. Well, how many of them are there? There are p squared, essentially, lines, given by the slope and the y-intercept. And then every point in the finite field has p different lines going through it. So I'm going to choose k to be p. And then sk is the entire plane, which has p squared elements. So L is p squared. So then if I compare, I have the size of sk is p squared, which basically is L squared over k squared. L squared is p to the fourth, and k squared is p squared. So this is p squared.
You don't have to compute because in the proof there is equality because every 2 points lie in exactly one line. So in the proof of the upper bound there is equality.
Yeah. Yes. Yeah. Uh-huh. That's right.
Smaller than p, then the other non-trivial theorems.
Yeah, that's right. If L is small enough, smaller than p, then there are non-trivial inequalities, meaning better than this. And one might wonder if they're as good as that. Oh, they're not.
I think they're somewhere in between.
I see, somewhere in between. OK, good. OK, well, so what's the significance of this? The significance of this is that the proof of this theorem is not going to be based purely on such statements as 2 points determine a line, and so on, because those are also true in finite fields. So it's necessary that it should use something which is not true in finite fields, at least not for this number of lines and this number of points and so on. And usually, well, in all examples, what it uses is something topological about the topology of R2. So these proofs, there are several proofs, 4 or 5 proofs. They all use a bit of topology. OK. So this is sort of the theorem of incidence geometry in 2 dimensions. And it's of course interesting to think about about questions in 3 dimensions. And it's maybe not obvious at first. It's not obvious at first what would be an interesting generalization of this to 3 dimensions. The first generalization that occurs to one is let's just take L lines in 3 dimensions. And it's worth mentioning what happens there, which is that exactly the same theorem is true, and it's still sharp. Oh, I forgot to mention, this is also sharp. And there's a similar kind of example that involves points in a square grid. OK, so this is also sharp. Right. So now let's try 3-dimensional generalization. Well, there's the following corollary. If L is a set of L lines in R3, Sk as before, then the size of Sk obeys exactly the same bound, L squared over k cubed plus L over k. And the proof is project to a random plane. So if I project to a random plane, I'll have L lines in it. Now, if I project to a poorly chosen plane, it could happen that 2 of my original lines end up over the same line. But if I project to a generic plane, this will not occur. So I'll have L lines. And if I take a point in Sk, it will land to a point that still has at least k lines going through it. And again, if I make a poorly chosen plane projection, then 2 points that used to be different in 3-dimensional space could end up over the same point. But if I do it generically, that won't happen. So that's the proof. Project to a random plane. It's still true. And it's still sharp, because R2 is sitting inside of R3. So whatever example was sharp before is still there. So this is, in fact, a not interesting way to generalize the Szemeredi-Trotter theorem to 3 dimensions. So now we can look back at theorem 2 and understand a little better what's going on. So we have n squared lines in 3 space. N squared is going to be the same as capital L before. But we have this extra thing. We have at most n of them in a plane. There are not too many in a plane. And that rules out this example. Right? We cannot just take our example from the plane, take all of those lines, because that would violate this condition that there are not too many lines in a plane. So that's one way of forcing genuinely 3-dimensional arrangements of lines. And then the question we're addressing is that if we have these genuinely 3-dimensional arrangements of lines, do we get a better estimate for Sk? And we do. This is going to be better than this.
So a general theorem like this would have more parameters, like you have some number of lines, and you have a bound on the number of lines in the plane.
Yeah, that's right. So in general, we could say there's extra parameters, at most b lines in a plane, and then the answer will depend on b. And
there also, it's known, you know what's the correct values are.
Yeah, we did. So we worked out in the paper this more general thing. And basically, the examples that make it sharp are this example is still sharp if it's allowed. And then you could put, b lines in each plane for a bunch of planes and use the 2-dimensional example and see what happens. And whichever of those is better is the best answer. Yeah.
Noticeably, this statement has only one term, whereas that one has 2. Is it because you don't care about the illustration, or?
No, it's because I insisted that k is at most n, which corresponds to insisting here that k is at most the square root of L. So we only see the first term. Yeah. And then if you could put bigger k also, and then what will happen is that term will reappear and it'll dominate. Yeah. OK. Good. Now, there's another direction that we could try to go to insist on really 3-dimensional incidence geometry, which is called the joints problem. And it was thought of by Sharir in the early 90s, I think. And this way of forcing things to be 3-dimensional is to force the incidences at each point to look 3-dimensional. So let's say we have L lines in R3. And then a joint is defined to be a point x such that there are 3 non-coplanar lines And then the joints problem is how many joints can there be? And of course, you cannot make a lot of joints by putting all of your lines in a plane, because then you'll have no joints. So the conjecture is that the size of the joint set is bounded by L to the 3/2, which occurs in, again, a cubical grid. And this turns out to be true. So let me give a little history. So Sharir and other people proved bounds with interesting but non-sharp exponents. They proved this kind of thing. And they were using the Szemeredi-Trotter proof technology. So I'll tell you after the break a little bit about how to prove this. And they were using that kind of argument. And it's not totally clear to me why, but it seems very difficult or maybe impossible to use that technology to prove the joints conjecture. And then there was an important breakthrough in important new idea in incidence geometry, which is called the polynomial method. And that was introduced by Zev in 2007. He proved Kakeya over finite fields. It would take me, I think it would involve mentioning too many. I already mentioned more problems sort of than I feel like is ideal, so I'm not going to say what that is. But it can be considered to be a problem in incidence geometry if you feel like it. Then based on this work, Katz and myself in 2008 proved the joints conjecture. And based on that work, Elekes and Sharir in 2010 proved theorem 2 for k equals 3. And these two things are very close to each other. So notice that if I consider there to be L lines, n squared is L, and k is 3, this bound is L to the 3/2, which is the same as the bound for the number of joints. These triples come in two kinds. So S3 is a point where there are 3 lines going through it. It may be that 3 lines are not coplanar. That would be a joint. So it follows just directly from this that there are not too many of those. Or they may lie in a plane. And that takes some more work, but they prove that if you have a lot of triples in a plane, then there'll be a plane somewhere that contains a lot of lines, and we have a bound on that. So they were able to get the full case here. OK. OK. So the polynomial method is a really cool method that resolved some old outstanding problems in incidence geometry, like the joints problem, or that. But it doesn't do everything. In particular, it doesn't do Szemeredi-Trotter. I remember Katz and I tried. We were very excited that we had this new method. And we said, let's prove Szemeredi-Trotter. And we tried it, and absolute garbage came out. And the reason it doesn't prove Szemeredi-Trotter is that Szemeredi-Trotter is not true in finite fields. And the polynomial method, since it's basically just based on algebra, and I'll show you. OK, I will show you what the polynomial method is after the break. But anyway, if you look at it, it seems like if it was going to work, it should probably also work in finite fields. It doesn't use any topology.
So the joint thing is true for finite fields?
The which thing?
The joints problem.
This is probably, though no one has written it down, it's probably true for finite fields with the same proof. This is also probably true for finite fields. OK, but the punchline of the first half of the talk is that this theorem 2 is not true for finite fields. So the reason that theorem 2 is difficult is that it combines all of the difficulties of the Szemeredi-Trotter theorem with the difficulties of the joints problem. So when k is 3, theorem 2 is almost the same as the joints problem. So it's going to be at least as hard as that. On the other hand, when k is large, theorem 2 is not true over finite fields in a way with basically the same example. It feels very reminiscent of Szemeredi-Trotter. And so it should be morally kind of as hard as this. So the way to prove theorem 2 is to combine these two ideas. So after the break, I'm going to sketch how to prove Szemeredi-Trotter. I'm going to sketch how to prove joints. And then I'm going to explain how to put them together to prove theorem 2. OK, let's relax.
When do we reconvene?
Let's reconvene, see how it goes. I've never given such a long talk. Okay, so I'm going to explain to you now one of the proofs of Szemeredi-Trotter, which is called the cell method proof. And then I'm going to explain to you the proof of the joints problem. So just sketching each of these, and then I'll be able to explain how to put them together. And that'll be my goal. OK, so the idea of the cell method is that I'm randomly going to pick some of these lines, and they're going to cut space into a bunch of regions. And then I'll analyze what happens in each region. OK, so I randomly pick L times k to the minus 2 lines contained in L.
This is probably not the shortest proof, right?
Yeah, this is not the shortest and not the first proof.
That's the middle.
But it's the proof that is going to be related to the proof of the theorem that I'm telling you. Yeah. So I'm going to randomly pick some of the lines. And then these lines divide space into cells. OK, so I have originally a bunch of lines. And then out of these lines, I pick a small sample. Maybe I have that, so on. And then the complement of that region is a bunch of polygons, which are my cells. And inside of each cell, I have some lines intersecting. And I'm going to, OK. So well, how many cells do I have? If I take that many lines, I'll have about the square of that. So I'll have this many cells. And now this following is a white lie that will help to explain the idea. So because I picked the lines randomly, we might hope that the points of Sk are evenly distributed among these cells. This is actually not true, but so the real proof goes a little bit differently. But this will help me to explain what I do later. So let's suppose that we managed to get that to happen. Let's say that there are a times L cubed times k to the minus 2 points of Sk. And so now we want to prove that A is not too big. So if we divide this by this, we see. Yeah.
Over k cubed. Somehow that doesn't quite match with the
L squared over k cubed. Yeah, thank you. It should be L squared over k cubed points of Sk. OK. And actually, I would like a few more random lines. So it's better to do this. A to the 1/2. So now I have that many cells. And so then when we do this division, we see that we have k points of Sk in each cell. OK. So next, I want to analyze how many lines there are in each cell. And the lemma is that there are at least around k squared lines that meet the interior of each cell. OK, so the proof of this is quite easy. There are k points of Sk in each cell. So let me say that x1, x2, and xk over 2 are contained in sk in the cell. And I could even have taken more, but actually it's prudent to stop at k over 2. Now, x1 has k different lines going through it. One of them may go through x2, and one of them may go through x3, and so on. But there are only k over 2 points here. So the majority of those lines don't go through any of these other points. So for every I have k over 2 lines through xi, and they don't intersect xj for j different from I. And I just add up all of these lines. So I have k over 2 lines for each of these k over 2 points. And I haven't counted any line twice, because these are the lines that just go through 1 point. So that's k squared over 4 lines. And that's all there is. So in each of these cells, I have about k squared lines going through the cell. And every one of those lines needs to go through the boundary of the cell. So what I'm going to do now is count I of LZ. So Z is the union of the random lines. Or another way of thinking of it is it's the walls of the cells. So I of LZ is the number of intersections between a line in L, which is not one of the random lines, and one of the random lines. Now, on the one hand, this ILZ is bounded from above by the number of lines in L times the number of lines in Z, which is a to the 1/2 L k to the minus 2. But on the other hand, the number of these intersections is bounded below by the number of cells times the number of lines in each cell. Because if I look at each cell, every line in that cell has to pass through the boundary of that cell somewhere. And that's true for every cell, so that's this product. And I haven't really overcounted any intersections by more than 2. OK, and the number of cells is a L squared k to the minus 4. And the number of lines per cell is k squared. So if we put this together, we get that a L squared k to the minus 2 is less than or equal to a to the 1/2 L squared k to the minus 2. And so everything matches up nicely, and we see that a is not too big.
Clarify what's your white line. This may go wrong by how much?
I think this might be even totally wrong. And the truth is that it's not the points that are evenly distributed between the cells, but the lines that are evenly distributed between the cells. And then there's an analogous argument. But it's going to be the points that are evenly distributed in the proof we do in a bit. Yeah. It looks a little magical, and I sort of don't like the presentation where at the end all of the algebra turns out right. But
So somehow for the lines it makes sense intuitively, right? Because if too many lines intersect the cell, then you probably would have chosen one of them with a random sample. That's basically the argument that goes into showing that not too many lines intersect the cell.
Yeah.
Yeah. And I think that VC dimension is also important.
OK. OK.
So it seems like you apply the trivial argument to each cell, and
Yes.
And the topology got used in the fact that there is a notion of region and cell.
Yeah, that's right.
Which is not what you can do.
Yeah, so the topology allowed us to say that there aren't basically, at least on average, there aren't too many lines in each cell. And then the points are distributed among the cells, and then you do a trivial argument in each cell.
So is something true for complex numbers? Szemeredi-Trotter type?
The Szemeredi-Trotter theorem is true in complex numbers, but I don't know the proof, which is harder. OK. So that's one kind of idea.
Why the topology was essentially
Well, you know, if I had some lines in a finite field, and then I looked at the complement of those lines,
the concept of a cell does not exist in
yeah, the concept of a cell does not exist.
But here you don't see how it does the work for you.
Well, see, I have the point here, which is in this cell, and I know sort of by counting that I have a line through this point. And then the topology tells me that this line has to pass through the boundary of the cell.
Yeah, you use it. Okay.
So that's where it's being used. Yeah.
We use the fact that the real numbers can be positive or negative. Because the idea is the barycentric coordinates that you
Sure.
Yes.
That's the point.
Yeah. OK. Yeah, it's somehow, you know, it's not it's not a lot of topology. It's hard to interest topologists. But from the point of view of combinatorialists or analysts or whatever, then it's topology. OK.
I think historically it was how the mean value theorem was phrased, no? That if you have a line in a triangle, it must meet the opposite end by both sun or something. Long ago.
Oh,
I think
uh-huh.
so. I'm not sure.
Uh-huh.
The opposite should be
OK. So I want to do a sketch of the joints also, say something about the polynomial method. There are a few different ways of doing this. This might not be the most elementary, but it's a certain spin on it. And so the idea is to think about algebraic structure. So when does a set of lines have algebraic structure? So for reference, a kind of basic fact of algebraic geometry is that if L is a set of L lines in R3, then there exists a polynomial P so that P is identically 0 on all of these lines, and the degree of P is at most like L to the 1/2. And one can find a sharp number here. This is just by counting coordinates, basically. The space of polynomials of degree D has a certain number of coordinates, and then if you look at the subspace where it vanishes on a line, that has a certain codimension, and then you just see how many of those you can insist on, and by linear algebra, find a polynomial that vanishes on that many lines. OK, so any old set of lines there's a polynomial that vanishes on it with this degree. So I would say that a set of lines has some algebraic structure if you can find a polynomial of significantly lower degree that vanishes on all of them. Those are special, and you could reasonably hope to prove something about them with algebraic geometry. So we'll say if the degree is a lot less than L to the 1/2, then we say that the set of lines has algebraic structure. So one way of thinking about the joints problem to get started is that if I had a hypothetical counterexample to the joints problem, a set with many joints, then first of all, it would have to have algebraic structure in this sense. And then once that's the case, one can use the algebraic structure to prove that this just can't happen. Suppose that I have L is a set of L lines in R3, and J, the set of joints, has size A times L to the 3/2, where I imagine that A is big. So a possible first step of the proof of the joints theorem is proposition. Then there exists a polynomial P of degree L to the 1/2 a to the minus 1/2, so the key point significantly smaller than there would be otherwise, such that P is identically 0 on L. OK, so here's how we're going to do that. So let me actually add. I'm going to assume. So I have a bunch of joints and a bunch of lines. I'm going to assume that the joints are evenly distributed. So assume that I have a times L to the 1/2 joints on each line. So to really prove the joints conjecture, you also have to worry that the joints may be distributed not evenly, but that's a minor point. So this is an assumption of the proposition. OK, so here's what we're going to do. We're going to pick a degree, which is smaller than L to the 1/2. And with that degree, we can arrange that a polynomial vanishes on a subset of the lines. So D, a degree to choose later. And then I find P, which is identically 0 on D squared lines of L, which I choose randomly. OK, but my assumption is that there are a lot of joints, which means that these lines are intersecting each other a lot. So if I take one of the other lines, it has a lot of intersections, and so it will go through these lines quite often. So let me say that these lines are L1, is my random set of lines. So suppose I look at a line L, which is in my lines, but I haven't arranged for the polynomial to vanish on it yet. Then, OK, so I expect L, so P should vanish on L at probably the following number of points. A times L to the 1/2, that's the number of joints, times D squared over L. So here's my line L, and it has a bunch of joints on it. At each of them, there are some other lines. There are A times L to the 1/2 joints. And then if I look at each joint and I ask, what's the probability that this other line was included in L1? Well, that probability is D squared over L, because I chose D squared random lines out of L lines. So this is the average number of places that I expect the polynomial to vanish. And now, if this number of vanishing is bigger than D, then I would have a degree D polynomial on a line that has more than D zeros. That would imply that P is identically 0 on the line L. So now we can unwind this equation and see what it tells us about D. The equation is A L to the minus 1/2 D squared is bigger than D. And we rearrange. And we get that D just needs to be bigger than L to the 1/2 A inverse. So it looks like it's a little better than what I wrote in the proposition. OK, so a configuration with a lot of joints has algebraic structure. It lies in a variety of lower degree than a general set of points. And we can use that algebraic structure to attack the joints problem. Think about how to manage my time. I think what I want to say for right now is that this is the beginning of the proof of joints, and that once you have a bunch of lines that you're studying and it has algebraic structure, that you have some tools that you might be able to bring to bear on it. OK. And then what I'd like to do in the rest of the time is tell you as much as I can about the proof of theorem 2, which is going to combine the cell method and the algebraic structure method. Does that sound reasonable?
So there will not be any additional topology, or so will be this course type?
There will be, yeah. There will be. OK. So after our long preparation, the main idea that I want to tell you about in this talk is a way of combining the cell method and the polynomial method. And the idea is that the cell walls are going to be made out of polynomials.
So just state again what you're proving. You're proving that the number of
Yeah, we're going to prove theorem 2.
theorem, okay.
Yeah.
Yes.
Okay. Okay. So I'm going to call this the polynomial cell method. The idea is that we're going to build cell walls that we use roughly the way we use them in Szemeredi-Trotter, but we're not going to build them by having some straight lines. We're going to build them out of polynomials. So to do that, I'm going to review a little bit about polynomials. So V sub d is going to be is the set of polynomials in R3, so in 3 variables of degree less than or equal to d. And that's, of course, a vector space over R. And the dimension of this V of d, V sub d, is going to be called n of d. Well, OK, this dimension of V of d is around d cubed. And n of d is going to be defined to be the dimension of V sub d minus 1. OK. And this basic fact about this dimension is important for trying to find polynomials that do various things. So, for example, an easy lemma is that if I have some points, x1 up to xn of d in R3, then there exists a polynomial of degree d, polynomial in Vd, such that p of xi equals 0 for all I. Non-zero polynomial, thank you. Yeah. So the reason for this is if I want p of x3 to be 0, that's a linear condition on the coordinates, on the coefficients of the polynomial. And so it defines a hyperplane in this vector space. And I'm looking at the intersection of a bunch of hyperplanes. And the number of hyperplanes is 1 less than the dimension of the vector space. So they intersect in at least a line. And that's how I get my non-zero p. OK. Now the next thing that we need is a kind of topological analog of this lemma, which is called the polynomial ham sandwich theorem. So that says that if u1 up to un of d are finite volume open sets in R3, then there exists a non-zero polynomial of degree d, so that now p is not going to vanish on an entire open set, but the substitute for that is that p bisects each ui. And I'll illustrate what that means by drawing a picture. So here's u1, u2, u3, u4. And then the vanishing set of p might look like this. So p is maybe positive here and negative there. And on each and every one of the ui's, p is positive on exactly half of the volume of ui and negative on exactly half of the volume of ui.
So you made them disjoint in the picture?
Yeah, so I made them disjoint in the picture. They don't have to be, but the picture is generally more confusing if you don't. And they will be when we use it.
This open set is, I mean, this, I don't know if this matters, since the polynomial could come back and hit the set again.
Yeah.
Is that a possibility?
That is a possibility. So the picture maybe might look really like this. And this could be also minus. Yeah, and the total negative part, whatever its shape, has the same volume as the total positive part, whatever its shape. Yeah, that's absolutely possible. OK. And now what we actually need is a corollary of this, where each of these open sets corresponds to a bunch of points. And we'd like to cut, we'd like our 0 set to divide the set of points about evenly. So corollary. So if y1 up to yn of d are finite sets contained in R3, then there exists a non-zero p of degree d, so that p bisects each of these sets yi. And what that means is that p is at least 0 on at least half of yi. And it is at most 0 on at least half of yi. So there are two ways that this could happen. Well, there are at least two ways that this could happen, but I want to highlight something. One way is that if my yi is those 8 points, the polynomial could divide them like that. But another thing that could happen is that if the yi are these 8 points, the polynomial could just go through all of them. The variety could just go through all of them.
All of them have odd cardinality, they have to hit 1 point from each set?
That's right. If they all have odd cardinality, you have to hit 1 point from each set, which you can do because of this, but you are also getting more. Yeah. So in this, if these were each singleton points, you would just have to hit each of those points, and you would have this. Yeah. OK, good. So let's orient ourselves now to prove this theorem. OK. The polynomial ham sandwich theorem has exactly the same proof as the regular ham sandwich theorem. The regular ham sandwich theorem you may have heard of. It just is the case that p is linear, which means that this pink thing will be a plane. And then in that case, we'll have 3 open sets. It has exactly the same proof as that, which is an elegant application of Borsuk-Ulam. And Borsuk-Ulam is a serious theorem in topology. Getting this corollary from this is also easy. Your open set is a bunch of tiny balls around the points. And then you take a limit as the radii of the balls go to 0, and this happens. But Borsuk-Ulam is serious. OK, so let's remember that L is our set of n-squared lines in R3, most n in a plane. And Sk is the set of points that lie in at least k lines. OK. Now, I want to basically try to use the cellular method that I showed how to prove Szemeredi-Trotter, more or less. So I would like to divide space into cells so that this set is evenly distributed among the different cells. And I'm going to do that by using this corollary to repeatedly construct varieties that cut the previous cells in half. Here's a picture. Maybe I'll start off by drawing. There are a lot of points, but I'll start off by drawing those. So the first step is that I pick P1, a polynomial that just bisects my set of points. And so I'm just bisecting one set. I can do that with a plane, and it's completely elementary, and it might look like that. now I've divided my set of points into two sets of points. So I have sk, I'll call them sk plus and sk minus. And my next step, I want to bisect both of them. So I choose P2 to bisect sk plus and sk minus. So that may look like this. And now I have four sets of points. And I will choose P3 to bisect the four sets of points. These first two, if you count, can both be planes. This one is not going to be a plane, but the corollary to polynomial ham sandwich will tell us how big its degree needs to be. So this will be degree 2. And to illustrate what may happen, I'll draw a picture that illustrates some possibilities. So we could happen that a lot of points lie on this thing. Right. This is actually a way of bisecting this region. Even if there's 2 here and none here, this is legal. Or could be, the more traditional way. So we have something like this. OK, and we're going to repeat this for a while, and then Pj is our last step. And we have 2 to the j different cells.
Do you care if the initial ones have low degree or if they can all have the same degree?
We do care. We will care.
So,
So we have now divided space into a bunch of cells using an algebraic variety. Namely, if P is the product P1 times P2 times Pj, and Z is the 0 set of P, then the Z is the cell walls.
I think what Michael was asking if the degree of this variety is not dominated by the degree of the last one.
It is dominated by the degree of the last one. But to do that, let me just do it. So, so P little j is required to bisect 2 to the little j things. And based on, so n of d is around d cubed. So if I want to bisect 2 to the little j things, p to the j, pj has degree 2 to the j to the 1/3. This is my degree dj. And if I cube that, I get 2 to the j, which is the number of things I want to bisect. So that means that the degree of p is the sum j equals 1 to big J, 2 to the j to the 1/3, which is like 2 to the big J over 3. It's dominated by the last term, like you say. So that's the degree of this variety that I've used to cut space into cells. And my number of cells is 2 to the j. OK, now at this point, I have to make a choice of j. And it turns out that it's good to choose that the degree is around n over k. So let me say that the degree is at most n over 10k and at least n over 100k. That'll be fine. And it's easy to check that we can arrange that for that to happen. We have enough. We can choose j so that will happen. OK. So that means that the number of cells is around n cubed k to the minus 3. And the number of points, right. OK. So there's now an important dichotomy in what happens in the proof. So as you can see in this picture, it could happen that the points lie in the interiors of cells, like this, or it could happen that the points lie on the walls of the cells. Those are both real possibilities. And there are 2 different cases. If all of the points are in the interiors of the cells, then the rest of the proof is very similar to the cellular method. I'll show you in a second. If all of the points are in the walls of the cells, it means that the set of points I care about is in a variety of what turns out to be quite a low degree. And then we'll check that also the lines will be in the walls of the cells, and that the lines will have more algebraic structure than you would expect, which is the beginning of the algebraic method. So I think that's what I'll be able to show in my time limit.
This is the example of where to screw around the perturbations, you could avoid the second case entirely.
The second case being the points where the points are on the cells.
Yeah.
It is. I don't think it's the case that we can avoid that.
You can have many points in one cell. If you move it a little bit, and all the points will fall in one cell. It would be even.
Anyway, you're allowed to perturb things here, right?
So
Because
if you're choosing polynomials,
No, but
But
it's
sometimes
just
that happens
kind of
with Katz and
yeah.
I. It's the only way to achieve that.
You want the splitting to be.
Yeah.
I understand.
Yeah. No, this is a good question. Let me say something about this. OK. So
Because in the examples you've shown, you can do that.
So in this picture, if we perturb this polynomial by epsilon, then these three cells are definitely going to be OK. Because these are safely positive, those are safely negative, and they're going to stay that way. Now, if we perturb this by epsilon, it's not so clear to me what will happen. It could be that this circle will just get smaller and they'll all end up on one side, which would be bad. Yeah. But on the other hand, I have some number of degrees of freedom, so maybe I can try to avoid that. But I could be in this situation. And then it's hard to avoid it. And in fact, we have examples where we know that it is impossible to cut points evenly into cells with polynomials of the given degrees.
Can you do that within epsilon?
Sorry?
Can you do that instead of evenly half and half, let's say half plus epsilon, half minus epsilon?
No, you still can't do it. Yeah, half plus epsilon and half minus epsilon would be OK for us, but you still can't do it. The problem is that if one problem is that all of the points could lie in a plane, or all of the points could lie in a quadratic surface. Say they all lie in a plane for a second, and I'm trying to cut them with a degree d variety. Now, I think that degree d varieties in three-dimensional space have d cubed degrees of freedom. But the intersection of my degree d variety with a plane is the only thing that matters here. And so that's a degree d variety in a plane. So I only really have d squared degrees of freedom. And because of that, it's not going to be possible to cut those points into cells as finely as I would like. OK. So these cases have names.
That is where you justify that the number of lines in a plane is small.
Yeah, that's right. That's right. So we have to use that somewhere. And that will come up in the case where a lot of points are in a plane. Yeah. OK, so the cell case is most points in the interiors of cells. And the algebraic case is most points in the walls. So let me sketch the cell case. OK, so the cell case, most of the points are in the interior. And so most cells have around the total number of points divided by the number of cells points in them. On the other hand, the topological contribution is going to tell us that most cells do not have very many lines. So the number of intersections between the lines and the variety is bounded by the number of lines, L squared, times the degree of the variety, So that's bounded by n cubed times k inverse. Now I have n cubed cells. So an average cell can only be incident to k squared. I have n cubed k to the minus 3 cells. So an average cell only meets k squared lines. Right. I had more than k squared lines in every cell. I had this many cells, and I would have too many incidences between the lines and the cell walls. OK. Now, if I have only k squared lines in this cell, then that bounds the number of points of high incidence that are in this cell. Someone said before that inside of each cell we want to do the trivial argument. The trivial argument from our current point of view, or the argument that we want to use from our current point of view is Szemeredi-Trotter. That tells us how many there can be. So Szemeredi-Trotter tells us that the size of Sk in a given cell is bounded by the number of lines in the cell squared over k cubed plus the number of lines in the cell over k. And the average cell only has k squared lines. So if you plug in k squared for L cell, this is bounded by k.
Yeah. So this you don't need, that's the trivial thing, you don't need Szemeredi-Trotter, right? If k points in each of them has k lines, then each of them has k lines of its own, as before. And there you have k squared.
Yeah, if you're careful about the constants.
Right, yeah. So just the argument that you had before.
Yeah, yeah. OK, so we're more basic. OK, anyway, so there are at most this many, but the number of points in each cell is around that. So we get Sk n to the minus 3k cubed is at most around k. And if you rearrange, you get the bound that we want for Sk. OK. So now let's think about what happens if we're in the algebraic case. So algebraic case. To get a feel for what happens, let's tell the white lie that all of the points are in Z. It's really just most of the points, but that's not a big deal. OK. Now, Z is the variety, the walls of the cell. Yeah. Let's say that the size of this set of points, all points means Sk, is a times n cubed times k to the minus 2. And we want to prove that a is not too big.
In the previous case,
Yeah.
how do you actually use the fact that the points were not in the boundary of the cells?
Well, it's in more cells. So you're not overcounting them.
Well, but
That's
it's
all
only
on
that
the.
too, it's not so bad.
That's a good question. All right, let's see.
For the
No, I don't think.
The
I
corners.
mean,
there
they are
can be
not on the
corners of
boundary.
many.
This is exactly this case. The case is that they are in the interior.
Yeah, but the question is, did I really use that they were in the interior, or could I have done everything with this argument?
How was this?
Yeah.
Could be points that are on the walls of many cells.
Could be points that are on the walls of many cells. That's an interesting one. If they're kind of on the, so the cells have kind of faces, and those faces meet in edges. These are all curved. A face only lies in 2 cells, but an edge a priori may lie in a lot of cells. And that could be the issue.
Also, in the partition, in the steps of the partitions, you have to decide which sets you're actually splitting. Some sets will be on the boundary.
Oh, yes, that's a good point. Yeah. So So in this picture here, what I actually did, although this could maybe be adjusted, is I bisected. Once a point is in the walls of the cells, I forget about it. And then I bisect this and I bisect that. So my next step may bisect those guys, do nothing very useful there, and bisect those guys.
So is the fact that you're like bisecting or roughly splitting them what's going into like the first sentence here? I mean, where is that?
Yeah, the fact that I'm bisecting every time means that every cell has at most this many points in it. Otherwise, all of the points could be in one cell, and all of the lines could go through that one cell, and then I haven't gained anything with my cells. So the cell argument is some kind of divide and conquer. It's necessary to make sure that I actually divided something. Yeah. That's a good question, though. I'm not positive if I've answered it. OK, so S sub k is around this big. And I'd like to know how many of those points are on each line. So each line has, well, n squared, right. Each point has, right, OK. It takes me a little while to do this correctly. So the number of incidences between sk and L is a times n cubed times k inverse, because each of these points, by definition, is contributing k incidences. So that means that if the lines are even, each line has a times n times k inverse points on it. The lines may be uneven, but again, it's a minor issue. Now, notice that this is bigger than n over 10k, which is at least the degree. If a is reasonably large, this will be bigger than the degree. And so that implies that the entire line is contained in the zero set of this polynomial. Now, remember that we have n squared lines. So if they were nothing was special about them, they would lie in a degree n variety. But they're actually lying in a variety of lower degree, n over 10k. And that means that they have some special algebraic structure. So the lines have special algebraic structure. OK. Now, in both the joints problem and in this, I haven't had time to tell you how to use that special algebraic structure to bound the number of points. But all I have time to say is that you do it in the same way. So those are, yeah.
Where do you use the fact that k is at least 3?
Yeah, OK. So I have embarrassingly failed to show you where we use all of the key hypotheses in our theorem. So, the statement, I've also erased the statement of the theorem. But the statement of the theorem says that k should be at least 3, and there should be at most n lines in a plane. And neither of these facts have appeared anywhere in what I've presented, so that's not that good. OK, so briefly, why is it important that k is at least 3? Suppose I have a point in a variety, and it has 3 lines going through it, which are all in the variety. Then that implies that this point has some special geometric significance in the variety. One thing that could happen is it could be a joint. That means the 3 lines are not coplanar. That means the variety does not have a tangent plane there. Variety has a tangent plane at a point. Then any line that goes through that point needs to lie in that plane. So if the 3 lines are not coplanar, that's a singular point of a variety. It's a special thing. And classical algebraic geometry will tell you that the singular set of a degree d variety is not too big in some way. And our singular set is big, because our singular set is this thing. And so if we exactly want to prove that it's not too big. Now suppose that the 3 points lie all in a plane. Suppose that the variety is singular, so it has a tangent plane. And there are 3 different lines that are all in the tangent plane. When I look at the variety to second order, so I approximate it by a quadratic, the lines all have to lie in the zero set of the quadratic. And a quadratic with negative signature has 2 lines where it vanishes. But a quadratic can't have 3 lines where it vanishes unless it's just 0. So a point where there are 3 lines going through a variety that are coplanar is a flat point, a point where to second order the variety looks like a plane. And those are also special. And there are also bounds for how many flat points a variety can have, except that there's one obvious thing that the variety could be a plane, in which case all of its points are flat. So, so this will tell us, this argument that I sketched will tell us that there are not too many singular points in this SK, and there are not too many flat points except for flat points that lie in planes. And there could be as many of those as you want. But then if you add the restriction that there are most n lines in a plane, it will bound how many bad points can come from planes. And that's the rapid fire, the rest of the proof.
Do all those features go through in a finite field setting?
They all require checking, and I would feel more comfortable if I knew more algebraic geometry.
But they seem to mostly involve algebra, right?
Yeah, they seem to mostly involve algebra.
They will go through, but then P has to be large. That's the problem.
No, wait a second.
Because so when you start doing the study of singular points and so on, variety, and say on a surface of degree, small degree, I mean, the things play. The quadratic characteristic 2 is not a good thing.
So say again?
The quadratic characteristic 2 is not a good object.
Yeah.
So you get those problems. So you have to start with the characteristic at least. And
But what would you do with this Borsuk, with a polynomial ensemble?
that's the problem.
This
That has no hope. Yeah, the cell part has no hope of working. But
you're asking about
Yeah,
what's
just
the
that,
second
just
thing?
the last few things he's talking about.
the last few things.
Well, but the statement for finite sets of the polynomial conjunction could be true for finite field.
Well, what does it mean?
No.
So it's ours.
The special algebraic structure, I mean, it's less clear.
That's true.
Sorry?
When you look at algebraic geometry,